All right, let's try another idea and let's try to work our way through this. And so another example of looking for the distinct roots or the nth roots of a particular complex number. Complex number I want to evaluate this time is just little old 8. And so to begin with, I need to rewrite that in its complex form and then transition it to its polar form. So its complex form was 8 plus 0i, and then its complex form was 8 times cosine 0 plus I sine 0. So I was able to take those 3 steps right there. Now I'm able to use this theorem that we've been working on from DeMoivre as far as try to figure out what are its distinct roots. And I want to find its distinct cube roots. So I know I'm going to be looking for 3 or values of k, 0, 1, and 2. I'm going to also do this in radians, although I could do it in degrees. I mean, yeah, we did the last one in degrees. We'll do this one in radians. And so let's just work our way through that. So I want to find my first value. Do we call them z's again? Z naught. So Z naught was n. N in this particular case is our 8. Our nth root, sorry, our nth roots that we're looking for is 3. So it's the cube root of 8 times the cosine, and the first one is theta plus 2 pi times k, which was a 0, all over n, which was a 3, plus I sine of the same argument, since it just repeats itself. Cube root of 8 is a 2. Cosine theta plus, that zero's out, or sorry, that's a 0, it's not a theta. 0 plus 0, so it's the cosine of 0 plus I sine of 0. That's the very first one, and I can reduce that down to more too. Cosine of 0 was a 1 plus I sine 0. Sine 0 is a 0 plus 0 equals 2. So there's one cube root that I found of 8. All right, another distinct cube root is, let's look for it at z0 or z1. So I'm going to go 3 root 8 cosine of this argument, which was 0 plus 2 times pi. I'm doing it at 1 now, times 1, all over 3, plus I sine of the same argument. Reduce that down, 2 cosine 0 plus 2 pi just gives me 2 pi, so I have 2 pi thirds plus I sine 2 pi thirds. And that equals 2. Cosine of 2 pi thirds is negative 1/2. Plus I sine of 2 pi thirds is I root 3 over 2. And then I can reduce that down, and that reduces down to minus 1 plus I root 3. So that's my second distinct root. And the third one, z squared, or z not, or z2. Cosine 0 plus 2 times pi times 2 this time, all over 3, plus I sine of the same argument. That equals 2. Cosine of 0 plus 2 pi times 2 is 4/3 pi. Sorry, no parentheses there. Plus I sine of 4/3 pi. Reduce that down. That's 2. Cosine of 4/3 pi. That's down in its first quadrant. That's negative as well, so that's negative 1/2. Plus I sine of 4/3 pi, and that is a negative root 3 over 2. Multiply through by 2, and that gives me negative 1 minus I root 3. So there are my 3 distinct roots that I have. And then if I were to graph those out on the complex plane, the first one's over at unit 2. We know these are all on the circle. They're all equal distance. The next one has an angle, so I'm looking at the second one right here, -1, so over 1 and up root 3, over 1 and up root 3. And this one's over 1, backwards 1, and down a root 3 distance. So here's Z0. Here's my second distinct root, and there's my third distinct root. All on the circle, all equal distance from each other, and they're all the distinct cube roots of the number 8 that I'm looking for on the complex plane. It's been a fun section. This kind of ends that particular chapter of stuff, and so everything we've been doing, this can be understandable with all the other tools we built up to this point. And so this is kind of your challenge part, is how well you're able to kind of process some of this information. So wish you the best.